libraries and stuff like that. So.
Give 2 minutes. Just wait a bit.
Yeah, sure.
Oh, this is the LVX.
What's this?
Is this LVX?
Sure. No, that's not mine.
Is this yours?
That's not. Someone left a lot of stuff.
If someone sees LVH, you could tell him that he forgot his bag and it's So you work on Debian and Ubuntu on the same packages?
Yeah. I actually started out in Ubuntu, and a lot of my work was sort of upstreaming stuff that Ubuntu was doing and stuff like that. And eventually, I just started contributing to Debian straight, and then I just sync back all my work to Ubuntu. So yeah, it's a pretty nice arrangement. A lot of people do that, especially these days. There's a lot of people who were Ubuntu contributors who start contributing to Debian, and in the end, help Ubuntu just by upstreaming stuff and getting the software code better. That's cool. Yeah.
All right. Guess we're ready to start.
Yeah, that's cool.
Let's do this.
All right.
Hi, please welcome Paul Tagliamonte. He works for the Sunlight Foundation and also on Debian and Ubuntu, and he's going to talk to us about how to implement Lisp front-end to Python.
All right. Hey, guys. How you doing? So I'm Paul, and I wrote a Lisp because I had a lot of free time and because I thought it would be fun. And hopefully you guys think that this is awesome as well, because I definitely do. So I work at the Sunlight Foundation, which is a 501c3 US nonprofit, which is focused on government transparency and accountability. And in my free time, I do a lot of Debian work, Ubuntu work, stuff like that, a lot of meta work. And every once in a while, I can be seen on Fluxbox, although a little bit less these days. The Sunlight Foundation is awesome. We do like a lot of government transparency, a lot of money in politics. And actually, the project that I started working at Sunlight, the project I was hired onto, was started at PyCon, and so PyCon means a whole lot to me, and especially Sunlight. And as always, we'll have OpenGov sprints. If anyone wants to join us for sprints, or if you just want to talk about Sunlight, you should talk to someone with a Sunlight shirt. I think we'd all be more than happy to talk about it. So, what is Hi? Which is a very good question. It's kind of a lot of things. It's basically a homoiconic S-expression front end to Python, right? You can sort of think of it like Clang compiles to LLVM, Hi compiles Lisp to Python. But it's just Python. That's basically all it is. Everything that you see in Hi is fundamentally just Python. Everything is just running as Python. It's pretty straightforward. Hi is super great, so let me show you how awesome Hi is. So you can see right here, I have a Python file, which is importing Hi and importing a module called maths. And I'm calling math square on 8 and then printing it. The maths file is actually written in Hi. And so this looks nothing like Python entirely, but yet Python is able to import it, which is magic and amazing. And so we're invoking the square function, which multiplies x by itself. Pretty straightforward there. And so when we run main.py, we get 64, which is amazing. No gasps. That's disappointing. Thank you. And it works so well, in fact, that if we import PDB, right, and we take a look at what's going on, we're in Python, but I want to step in to see what's going on, and we have a Lisp. This is awesome, right? Like, sweet. Like, no, man, like X, look at that, it's 8. Like, this works great. Everything works great. It's incredible. And so it is possibly the most Pythonic Lisp that has ever existed in the history of ever, and I hope it'll stay that way, because it's awesome. Like Hi and Lisp in particular lets you write incredible DSLs, domain-specific languages. And so I've written a couple of pretty cool ones, something called Snitch. Actually, I'll get into that one later. Something called marks, which is a DSL, a domain-specific language to control Docker, because I really love Docker a lot. And lets you control the means of production. Get it? Thank you. Boo, thank you. All right. So thank you. All right. And so basically, it's like 3 lines of pretty simple Lisp, but yet when it's run, the translated code, this is sort of reverse engineered Python. It's generated off of the stuff that Hi generates. Looks like this. It's crazy. But fundamentally, it just, I mean, this is async IO Python 3.4, and like all you have to do is write 1 line. It's awesome, and you can write all sorts of crazy stuff. Don't tell Guido; he'll like kill me. And so basically, I wanted to give this talk because Hi uses a ton of Python internals in a super Pythonic way. And so Hi is a really good narrative to give a talk. So the end goal is to create a Lisp-like that's able to be run with these sort of features that you can debug it with PDB. Python can import it, think it's Python, introspection works, and everything that you're getting is function definitions and stuff. And it's a pretty good narrative for giving a talk about these internals. So let's talk about how it works, because that's really the interesting part for all of us. So let's talk quickly again about why I created Hi. And it was basically because I wanted a language to finish some of the research I was working on in college about decentralized algorithms, which is awesome. We'll talk about that all day if someone wants to come up to me afterwards. And I want to do it through the healing power of macros, which basically let you do insane stuff. It lets you rewrite the language. You can add features to the language that weren't supposed to be there. And it's great. Once you start using them, they're very dangerous. You get into like macro OD mode. You just start like putting macros everywhere. No one can read your code, and then you figure out the right place, like when to use them. And then once you're there, things are great. And so a super cool DSL that I wrote early on was something called Snitch, which is an entire DSL built to monitor servers, because I think that's a really annoying problem. And so this is what some Snitch DSL looks like. You basically say the rules file, these are the rules for the Debian suite of things. I'm going to declare rule for the SSH server that it has an open port 22. I have these other servers that are pingable and HTTPable, like pretty standard generic stuff that's pretty boring at its core. But it lets you define them very declaratively, and basically it turns into 3.4 async IO code, because I really like async IO a lot. And so it turns into this code here, which is basically where it goes through. It hits all these servers. It's a mess, but like this is all compiled. This is behind the scenes. But it'll go through and hit all these servers and store the result in Mongo and let you get at them later. And so you can declaratively write source files that are very easy to understand and very powerfully generate massive amounts of code, which may be what you want or maybe not what you want. But I mean, every tool kind of has value. So. And if I can do this with Lisp, with Python, think about what you can use it for your own projects. Doing AST voodoo is obviously not the first thing that you should jump to, but once you find the right use case for it, it's pretty powerful. And it's definitely a really nice tool to have. And also, Hiling is super cool. Anyone who's interested in it, we can talk about it all day. Shout out to all the Hi authors who have done some amazing work on putting all these pieces in place. Jay King, woohoo! Jay King, who's, oh, there he is speaking after me, actually, and he's one of the Hi contributors. And we have about 50-something now, which is insane. But they've done such great work, I can't possibly take credit for all this. So we have a stream of Hi source code. How do we end up getting to Python bytecode? We need to take stuff like print 1+1 and turn it into sort of Pythonic representation, Python objects that we can work with because the compiler itself is in Python. We need to tokenize them. If you guys will notice, in Lisp, all the operators are the first thing in the parenthesis. So you can see it as +11, which is usually written as 1+1 with infix notation. This will take an arbitrary number of parameters, so +1,1,1,1 will be 1+1+1+1. And it's pretty simple once you get it, but it can be a little bit ugly, so just bear with it. Once it clicks, it'll click pretty hard, and it's a pretty powerful concept. And so we want to turn them into Hi expressions, Hi symbols, Hi integers, stuff like that. We just want to break everything down into these tokens. The exact objects that we have aren't really that important, but we have stuff like lists, floats, integers, dicts, keywords, strings, symbols, expressions. Pretty simple, but we just need to be able to express all the objects that we're going to be getting in sort of Python objects. This is Hi's version of AST. Get into that in a little bit. But basically, we'll lex it and parse it. I don't want to get into all that right now because it's definitely a topic on its own. Shout out to Nicolas Tagliamonte, who did the parser work for Hi. He did a great job with it. Also, shout out to Alex Ganner, who I know isn't here, but for writing rply, which is what we use. We had Parsley originally, but we ended up switching to rply. And basically, we use rply as like little callbacks that let us, when we get a matched string, they'll call back to us and we can instantiate an object. And then we can use that to generate the tree that we actually generate code off of. So don't worry too much about that. That was a pretty high-level view. Basically, we take the input of characters, we'll take the input stream of bytes, and we'll turn that into a hierarchy, the sort of programmatic representation of Hi itself. So all the Hi objects, so we have the lists and the dicts and the names and the symbols. And so basically, we have this organized tree of everything that we care about, and we actually want to do something with it, like run it. So let's start getting into how we can turn this into Python bytecode, because that's really what we want. Because writing in like virtual machines is boring work. Not to offend Larry, who I see in the front there, but writing interpreters for bytecode is terrible, and you should avoid them at any cost. And so I just want to generate Python bytecode. It's just not really what I want to get into. But like bytecode's hard. I don't really want to generate bytecode because it's such a pain. I don't want to assemble all this, and it changes constantly. It's not a public interface. Like I'm not going to depend on a single version of Python. It's not stable. It's not great. I just don't want to. I don't want to directly write out bytecode. So what we're left with is the AST module. And the AST module is sort of like a step above bytecode. It's Python's representation of Python. It's how Python thinks of itself. And it's available on most platforms, kind of. If anyone was playing around with the JavaScript-based, or I should say JavaScript for anyone who was at Gary's talk, that doesn't have the AST module available. I tried to port it. But basically, most platforms have some version of the AST module that you can abuse, which we do. So let's talk about Python AST, because this is clearly one of my favorite parts about Python. It's just amazing. It's totally cool. Don't worry about it. Whatever you've heard about the AST, it's great. And used the right way, it can be really powerful. The AST is fundamentally just like Lisp macros. People that talk about how great macros are aren't really talking about how great Lisp macros are. They're talking about how great code is that can alter other code. AST lets Python code modify sort of parsed Python code, right? Python thinks of Python in the AST. So when you store the tree of a Python source file, so all the expressions, all the statements, all the if conditionals, all the function definitions, everything is expressed in the AST. It's sort of a very fundamental part, and it's brilliant. It's really good stuff. So let's take a look at some AST. This is possibly the most straightforward example that I could possibly think of. It's an ast.name, which is a Python like a name. Anything that a variable, you do foo equal 1, foo is the name. And then we're giving it an attribute ID, and we're calling it state. And so this is a variable named state. So if we were to do state equal 2, then you would use an ast.name ID state, and then you'd assign that to the integer. So this is extremely simple, and you can see that this is sort of how Python is representing itself, right? When we think of a variable, we're actually thinking of an ast.name. Now, if we look at a list, we have an ast.list, which contains an actual Python list, which is kind of funny, but great, of ast.num elements, which have different values in the n attribute. And so we can see else, and so given a list of 1, 2, 3, 4, we can see that we have an ast.list of ast.num n equal 1, 2, 3, 4. Pretty straightforward here. It's kind of goofy to have to use a Python list inside an AST list, but that's just the nature of the beast. Now, if we looked at a dictionary and how they're defined, we have keys and values, and these are just zipped up when it's being built. And so even though they're ordered here, they're not necessarily ordered once they're built into bytecode. But the dictionary contains a keys attribute, which is a list of the keys. So you can see at the top we have foo, bar, baz. And then we have their values, which are 1, 2, 3, 4. So foo is 1, bar is 2, baz is 3. And so we can see how we can take an arbitrary Python expression, like a dictionary expression, and how we can turn it into AST so that we can programmatically deal with it in Python itself. It is extremely meta and great. And so now let's get to something that's a little bit more practical now that we have kind of the basics down here. A function definition, which isn't so bad. So we have def square of x, return x times x, or optionally the Pythonic function there, square x, x times x. And you can see that we have a function definition with a name of square, because the function name is square. You have the arguments being listed out here. So we have x. We have no var args or quargs. We have no defaults. And the body is simply return a binary operation of x times x. You can see that we're using the name here. And so that'll return, I mean, obviously, this is just the representation of the function that we define there. And so regardless of Hi or Python, it'll compile to equivalent AST, which is pretty neat. The AST is not a guaranteed interface. It's definitely not. It's great, and you should consider it whenever you have a problem that warrants the use of the AST, but it's definitely not sort of a stable, exposed part of Python, the language. It has broken, it will break again, and I mean, it's just sort of the nature of the AST, because it is sort of an implementation detail more than sort of a public piece of code to be using. That being said, it's not terrible to work with it, but it can completely change between minor versions or different implementations. So CPython will be different than PyPy or Jython. And minor versions, so for instance, between 3.2 and 3.3, try except and try finally were moved into a single ast.try, which is great. And it definitely sort of represents the situation better, but it's definitely not the case where stability is guaranteed. So definitely be careful and watch out for changes in the AST on different versions of Python. That's sort of one thing to keep in mind. But that being said, you can get away with it. If you want to talk about different techniques to get around sort of the AST's changes, I'd be happy to talk about you with them. Luckily, a lot of the attribute changes were not conflicting, so you can just overpopulate everything, stuff like that, and you can get around a couple of the changes without having to be too concerned about them. But definitely come up to me if you want to talk about AST and how to avoid breakage, because it's definitely a fun topic. And if you start trying to get things, so for instance, Hi has compatibility between 2.6 to 3.4, and maintaining that is can be a little bit of a pain, but it's not so bad. So I just want to get into a couple of philosophical notes on the AST, just sort of general notes surrounding the usage of the AST. It will break compatibility, but like I said, it's not that hard to work around. Attribute names were changed almost completely between 2 and 3 for the better, I think. But they definitely were changed in your code, has to keep that in mind. If you do want to support 2 and 3, you can just populate all the attributes, like I said, and forget about it. And it's a little bit more expensive during compile time because you have to create these objects with duplicate data on the on different attributes. But once it's compiled, no one really cares. So you can definitely get around some of the breakage that way without having conditionals all over the place. And definitely be ready to segfault Python. Yes. Because you can create crazy things with AST that bear no resemblance to real life or sanity. You can create like arbitrary AST trees that make no sense whatsoever. Python will try to execute them in segfault. So if you're ready to do some AST work, be ready to see a segfaulting Python. It's not super bad once you know what's going on. You can kind of isolate it, and when you make a change, you can kind of keep in mind, well, okay, that doesn't make sense. But in general, if you just stick to pretty sane changes, it's not going to be super bad. There's actually a super nasty bug that we hit in Hi where we were trying to debug the segfault, but because we were running in debug mode, Python was doing additional checking on the AST and segfaulting in a completely different place. So that can definitely happen. AST also shouldn't go backwards in line numbers. I tried to do this, and it did not work. CPython will let you get away with it if you're not running in debug mode, but PyPy will just explode immediately. I wanted to move a couple of statements from a line in the middle of the source tree up to the top. Python did not like this. So try to keep your source code going forward in lines, and everyone will be much happier, that's for sure. Yeah, like I said, CPython will tolerate it, but PyPy definitely does not. Another thing to note is that all expressions in the AST are either a statement or an expression. The difference between these is pretty straightforward, but stuff that sort of inherently has value, like an integer or a lambda expression, this is actually kind of a weird one, but a lambda expression, those are expressions. They're things that you can stuff inside a print. So if you can do print paren, like 1 plus 1, you're probably dealing with an expression. On the other hand, with a statement, if you try to print def foo paren colon, like there's the syntax error because it inherently means nothing. If you're trying to do print paren if true, then you're going to run into problems. And of course, there's an inline version of if, like print foo if bar else baz. That's an expression. And so in the AST, keep in mind that expressions need to go where expressions go, and statements need to go where statements go. And that line can be a little bit of a pain if you're running a Lisp, because everything's supposed to be an expression. So basically, things that control flow, function definitions, those are all statements. And like imports, those are statements. Stuff that you couldn't throw into a print, basically, is going to be a statement. And so bear that in mind when you're working with the AST. This definitely makes early high work pretty hard because we obviously want expressions everywhere because it's pretty common to stuff an if statement inside a print or something like that. And so we had to fake this everywhere. If you want to talk about techniques on faking expressions everywhere, again, I'd be happy to talk about that with you. There are a couple of tricks that you can do that make this a little bit more palatable. In addition, on the AST, it contains a little bit of meta information. And the meta information particularly correlates blocks in the AST to source line numbers, which becomes very important. This actually gets copied into the code objects later on. And it basically lets Python itself know where a particular piece of code came from so that when you raise an exception, it can show it in the tracebacks, or PDB knows where to look for it. Pretty sane stuff. So if during the high compilation, we maintain the line numbers and stuff like that and annotate the AST that we generate with proper line numbers so that exceptions will show high source code and the PDB works and stuff like that, which is crazy, but I mean, nothing cares, it's just printing lines. And yeah, like I said, it's basically just used down the line when you're looking at doing stuff like exceptions or debugging. If you run optimized, actually might not be -o, but one of the optimization levels will strip out line numbers, not just stock strings. Yeah, there's only a very particular way that you could run code without the annotated numbers and line numbers and stuff like that. But it can definitely be done, so they're not always present, but they're good to have. They're great to have, actually. So why should we care about AST is the bigger question, because that was a little bit dry, and I sort of threw a lot of AST at you so that you'd have kind of an understanding of this, and I'm sorry for that, but basically the AST will let you start approximating DSLs in Python, which is hearsay, and I think a lot of people would think that's a bad thing to encourage people to write DSLs in Python, and it may be, but I think that we should know and explore the topic a little bit more. You can imagine a declarative syntax, some like config file that you have that you could trivially turn into a Python function. So for instance, if you take these rules in, and you could generate AST that's a function or something, and then you could return that function back to the thing that imported the config file that lets you apply this function over data. So rather than having this clunky object-based API and like messing around, you basically take a config file and turn it directly into raw Python and then be able to use that. It's kind of a crazy idea, but it could totally work. You can take anything, any sort of syntax that you can think of that might be used at runtime, you could probably generate AST for it. And do some pretty crazy stuff. But no one uses AST for anything like that, which I think is disappointing. I think that we should look at AST a little bit more, because I think AST is great. And it's definitely one of those topics that's a little bit confusing, and people tend to get frightened pretty quick, but I think it's something that we need to look at. So let's stop for a minute on the AST, and let's move on a little bit. So we have this AST, so we've taken the Python source code, we've built it all into the high objects that we have, and we've turned that into some random jumble of Python that is equivalent behavior to what we want, right? So that's essentially what we did with high. We take all the source code in, and we dump out huge amounts of AST. What we want to do is we want to use that AST to actually run code. So let's massage it into something that we can deal with. Oh, what was that? Oh, God. Oh, no. Oh, no. Oh, that is a complete failure. Sorry, guys. I do not know how that happened. Where was I? OK, right. So, sorry, I lost my train of thought completely. That was weird. Let's say that we have this jumble of AST and we want to actually do something with it. So you can imagine that our compilation step outputted something like this, which is a module. So it's a Python source file, basically. And we have a single expression inside the source file, which is calling print hello, which is not quite hello world, but it's close. And you can see here that we have line annotations and column annotations. You can see that everything looks as you'd expect it. Obviously, feel free to sort of go into AST a little bit more, but I'm not going to get into that entire thing right now. But basically, what we do is we're going to run it through the compile built-in Python, which takes either raw source or we can give it AST. The source file it came from, which that is wrong, but that can be wherever it came from. So in the case of high, we'd have like test.high. Or sometimes you'll see people use angle bracket, stdin, and angle bracket. And then there are a couple of different things that you can use. There's exec, if you just want to exec the code, a val if you want to actually get a value back, which takes an expression. And single, I think, is the other one. And then if we take a look at the type of the thing that the compile step returned, you can see it's of type code. And then we can exec code to actually run the AST. So this is the step to take AST from Python objects and to turn it into the actual runtime. So we undergo the compile step, and then we exec the code. And so the key steps here are essentially the compile, which takes the AST source string, file name, again, for runtime errors, stuff like that. If we want to actually look at the source code, then we know where to look. Exec, if we have an entire module. Single, if we have a single statement we want to look at, or a val to a valid expression. Sorry for the poetic reading. It's just this is pretty standard stuff. And the exact type returned by compile is a code type, or type code. And from the doc string, it's basically just bytecode, total bytecode. And if we look at the doc string, code object, not for the faint of heart. And they're kind of right. Definitely beware dragons. That's definitely a pretty scary module to get into. But once we have the code module, which we've generated off the AST, which contains the actual bytecode for the Python virtual machine, the actual things that it's going to be executing, the actual statements like jumps and all the branches, condition. I'm not going to get into it. I haven't looked too much at the Python bytecode, but it's nasty and awesome and great, but nasty. And basically, we can exec or eval it. And the signature that we use to run the actual exec is we give it the code globals locals, where locals and globals are dicts that represent the environment. You may recognize those names if you've called locals or globals. And the fun part about this is when you exec stuff, you can put anything in there. So you can add crazy stuff into everyone's environments and do terrible, nasty things, and no one will really mind except for people whose code you break. But you can set all sorts of crazy stuff inside locals and globals, and you're sort of controlling that, which is awesome. But again, it's awesome, but a huge pain to generate manually, so don't do it. Let Python do it. It's going to save so much pain. And code, actually, is the exact stuff that's found in the PyC files. It's just been pickled, actually marshaled with a couple of headers. Exactly, it's pycompile magic, or import lib util magic number, the timestamp, file size, and a marshal dump of the code object. If you were here for Alex's talk, you should know why pickles and marshals are bad, except PyC files are fine because you're executing it anyway. So it's perfectly reasonable to use marshals of the actual code objects here. But essentially, all that's in a PyC file is a couple of headers and then one of these code objects. So fundamentally, they're not scary at all, and they're just little bits of Python bytecode shoved into a file with a little bit of metadata. Which works for any AST you generate, even high. So later on, if I stuff it into a PyC file and then just let Python deal with it later, it can just import it using the normal import process. It's so good that I could take it, move it to a different machine, and that machine would just be able to import the PyC without an internal dependency on Hive, which is crazy. But any AST that you generate, you could write out to a PyC file and just let Python handle without invoking sort of the overhead of the AST compile step again, which is awesome. And basically, every version of the interpreter may have their own version of what is in the PyC file. And so definitely know that's a sort of Python-dependent version. Python-dependent particular bit of magic there. Which leads me to talk very briefly on a tangent about PyCache, because I think it's worth mentioning, which is that the PyC file setup changed a bit in Python 3. In that they're stored in a directory instead of just as filename.pyc. This was done basically so that you could have different versions of different interpreters storing all their PyC files together without having every interpreter invalidate the other PyC files and having to regenerate them all. And so in that case, inside PyCache, it's name interpreter version. So if we're in a file called importer.py, the PyC file that you store out would be importer.cpython-34.pyc. Pretty awesome. So just know that if you are trying to do terrible things with PyC, you should take this into account. Totally great, totally awesome. You should play with all this stuff because it's great. All this is just awesome, and you should look at all of it. So let's talk about how we can make Hi actually importable, because you could see at the beginning here, when we looked at the source file in main.py, we were able to import Hi and then import maths. And we actually ran this. We get the, oops, I forgot to dump the PDB off. So we actually run this, we'll get 64. But if we remove this Hi statement, so if we remove import Hi and try to import maths, it can't find it. So how did we do this? This is crazy. Potentially confusing, but awesome. So what I abused in particular for this is PEP 302, which is new import hooks for Python. It was developed for the very noble cause of letting stuff import out of zip files and stuff like that without having that actually be part of, you know, like the actual importing magic, because that's a pretty disastrous place to put it. And so you can use it for anything, though. So rather than just zip files, you can imagine an importer that, like, if you import com.pultag.foo.bar.py, it would actually go out on the internet, get that file, bring it back, and run it. Don't do it. Don't do this. No one do this. No one get any ideas. But you could totally do it. And it would be terrible, but you could do it. And basically, this exposes import lib internals to you, and you can hack onto this during runtime, and it lets you do all sorts of crazy things. So it was definitely originally intended for something noble, but it's just generic enough for us to abuse entirely to import Lisp. So let's talk a little bit about 302, which is one of my favorite PEPs. 302 is composed of finders, importers, and loaders. And basically, the key part here is that we have an importer, which figures out whether or not it can actually import something, and the loader, which actually imports something and puts it into sys modules. It just takes the code, stuffs it into sys modules, and it's done. Importer objects just define a method called loadModule, which either return a loader object, which can import the particular piece of source code that you're interested in, so like OS or sys, or none if it can't do it. So if you look at all the possible places that you could import from somewhere and say, no, I'm sorry, I know nothing called OS or sys, then you can just drop out with a none and let the standard mechanisms take care of it. If you want to see a sample one, you can find it at hiimporter.py in the hi source file. Basically, it searches sys.path for .hi files instead of .py files, which is awesome, because then you can just use the normal sys.path, and you can shove stuff up into PyPI, and everyone's happy. And you register importers by appending them to the sys meta path. The sys meta path is actually searched before the normal Python path. So if you wanted to create something that would alter AST before Python gets a chance to import it the normal way, that's probably how you do it. Yeah, so it's searched before implicit or default finders on syspath. So, and again, sorry, I just completely ducked my slides here. And so we just load hi files from behind Python's back, shove it into sys modules, and Python knows about it. No one will ever know. No one will know. It's great, because Python just thinks it's Python, because we're shoving Python bytecode into sys modules. The only thing that would look weird is if you're looking at the file, because the file name doesn't end with py, but neither do PyC files, right? So basically, PEP302 is amazing and awesome. It's totally ripe for abuse. Someone created a module, I can't remember what it was called, but basically it would let you import this module, and then when you imported anything after that, every single statement was wrapped with a try except pass. So you couldn't raise exceptions. So you can like run terrible code, trigger an exception, it'll just keep going. Like, don't worry about it. Like, it's fine. Yeah, okay, it was called fuck it. Right, yep, that's it. Don't use it. So basically what we can do is we can take something written in hi on the path. We can take that hi code. We can turn it into AST. Then we can turn that into bytecode by using the compile step, and then run it as if it was native Python. Just amazing. I paced that pretty bad, so I ended a little bit early. I'm sorry about that. I can talk more about any topics. So I can take some questions or something like that, or keep rambling about different parts of hi that I find interesting. So
I have a question for you.
Sure.
You've Lispified Python. You've done really cool things with the syntax. You've added macro support. Have you done anything else to the semantics of the language? Have you made scopes immutable or done anything else?
That's a really tough question for me to answer, because it hurts me inside that I haven't. Stuff like non-local, which is in Python 3, would be really nice to have in Python, and finding ways around that is a little bit painful. So there are a couple of known hacks and ways to get around it, but they haven't been implemented yet. It doesn't mean they can't be done. It just means they haven't been implemented yet. The primary concern of hi is basically making sure that hi is sort of bidirectionally compatible with Python, which is different than Clojure, right? Because Clojure cares about unidirectional compatibility. It cares that Clojure can use Java, but not necessarily that Java can use Clojure, because that's a very hard thing to do. But hi cares about both directions. And so maintaining sort of keeping it pure in the Lisp sense and keeping it pure in a Pythonic sense are sort of mutually exclusive to a degree. And so finding a way around that is something I'm interested in, but not necessarily something that has any sort of implementation behind it right now.
How stable or production ready is hi right now?
So at my lightning talk last year where I talked about hi, I think many of you may have remembered me giggling and talking about how terrible it was. I still agree to some, on some level that it's probably not ready to be thrown into production, but people have. That ship's definitely sailed on me. And so people, there's one Debian hacker who ended up deploying it at work as part of their firewall system. He wrote a library called Adderall, which was high on Adderall. And which basically was a mini Quran implementation, sort of the logic, constraint-based solver, and I think is using that for packet filtering, which disturbs me on so many levels. But it seems to work, and I mean his coworkers don't know, so. But I wouldn't call it entirely production ready, but people have done it, so you wouldn't be alone.
So you touched on very quickly and said, I don't have time to talk about it, so you can ask me later. I'm asking now about statements, wrapping statements in expressions.
Yes, okay, great. Thank you, Larry.
Yeah.
Awesome. Thank you, appreciate it. I have to fill up my talk a little bit. I ended a little bit early, so I'm sorry. So essentially what we do is when we detect that we're actually going to start, actually we don't even detect. At all points, whenever we have a statement, we actually don't return the AST objects raw in the compiler. We end up returning a wrapped object, which is a high result. And this result contains any statements that are included in it, and then a single expression that references the value from that statement. So for instance, in both so if we have an if statement, we'll have the true branch and the false branch, both of which will be assigned to a transient variable. And so if you need the expression referenced by that statement, then it'll return you the name referenced by the value of the last thing in that statement branch. And so with a function, it would be the function name. With an if branch, it would be each branch of the if. And it's actually pretty clever. My original method of doing it was a lot more hacky, but it seems to work pretty well. It generates nonsense names all over the place. But it ends up working really nice. Whenever you want to put an if statement inside something, it'll just rearrange them slightly. So.
Hey, so I'm the co-author of Exoset, Parsley, and Monty.
Sweet, thank you. We used Parsley for a while, and I really appreciate it.
I want to know, in Parsley and Monty, we generate Python code, and we do it with a lot of string manipulation instead of with AST. And I know this makes you grimace, but for two reasons, the one being AST compatibility and the other being compactness and terseness, we found that string manipulation is relatively superior, which is not to say that Python code generation on the fly is fun at all, but we had to do it one way or another, and we picked this way. Did you try string manipulation before going to AST?
So when I first started working on High, I asked Ned Bouchelder about some of this stuff. I think his response was, don't use the AST. And I think that's probably a fair thing to say in a lot of cases. And he mentioned, like, obviously the Python syntax is the stable interface to the language. Why wouldn't you use that? You know, as inferred, you dummy. But, I mean, obviously he's much too nice to ever say that. And so basically, yeah, I started to look into how to generate, like, Python source. But it started to get pretty painful pretty quick because we're doing some pretty nasty stuff, and we do rewrite code as we go forth in the compilation process. So if we reach particular cases down the line, so for instance, decorators, we'll have to go back and decorate the function that we're actually decorating. It makes it just a lot easier if we work with the AST. And plus, I really like the AST. It makes generating readable Python to debug a lot harder. But there are a couple of Python modules that generate pretty sane Python off of the AST that are pretty useful for debugging, even if they are potentially invalid. So.
Cool, thank you.
Sure.
First off, you're a very funny guy.
Thank you.
But so, question about, like, you mentioned it's segfaulting all over the place?
Yes.
So, is that a matter of, like, you can just write any sort of high, and, like, there's a chance that it might segfault if you write something weird, or is it, like, if you use only the language constructs, it's safe, but if you write your own macros, it'll segfault, or it would segfault during development, but we figured out how to make it not segfault until they release a new Python version.
Right, right. So actually, yeah, High will never segfault on you unless you're actually changing stuff on it now. But during development, when you're actually working on the AST generation code, if you end up putting stuff in an awkward position that isn't necessarily something that Python handles as part of, like, the normal runtime, it may potentially segfault. Actually, it may always segfault. So for instance, if you try to print, like you use an ast.print on an ast.functionDef, I think it'll segfault, which is not possible when you're using the High language interface because the compiler is smart enough to know I need to avoid this by doing this special thing. So it's extremely rare. I don't think it's possible anymore to segfault Python from the high language itself, but in development, if you're messing around with the AST tree, you can definitely cause some segfaults. So.
Okay, so like I could make a web service for try high, and people wouldn't be able to just upload code that segfaults my server.
Yes, and what an awesome name that would be. There's tryhigh.appspot.com, which someone wrote. And it actually runs on Google App Engine and uses their sandboxing, because I don't think any one of us feels that ambitious right now. But definitely, we should talk about that. So, yeah.
So one thing we care a lot about in Mercurial is that we want the imports to be really fast, and also any kind of program where it's like a short program and you want the low responsiveness when you're running a Python program from start to finish to be fast. That includes the imports. I'm just wondering, are the imports or the compilations in high significant?
The answer is it depends. It started off being trivial, and I think to some degree it's still trivial. Obviously, there's an overhead compared to Python. That overhead, I think, is minimal and acceptable. But there's definitely a very small overhead, and for some reason there's a massive overhead when doing certain edge cases. So running our tests on PyPy takes a really long time in some weird situations I'm not entirely sure about. But I think those are almost definitely a problem with the interpreter, not so much the process.
Just PyPy, because PyPy is also slow for some things for us.
What's that?
PyPy is also slow for some things for us. Slower
yeah, interesting.
Sometimes it's slower than, say, Python.
Yeah. Yeah, just PyPy for some reason. But the overhead is fairly minimal, in my opinion. And it's also possible to write out PyC files. It's actually part of the language. And so then there's no overhead on the second time. But
okay.
Yeah. I think that's it. I think I got the stop. Yeah, I got the stop. Oh, no, Drew. All right, we'll talk later. Cool. Thank you so much.